Okay, so what we want to do here is we have the equation y to the fourth equals y squared minus x squared. And if we look at the graph here, it makes like a figure 8. And so I'll zoom into that real quick so we can see. Now I did it on my graphing, on my website. I have a graphing calculator there, and it makes it a little easier for us to graph mathematical relationships that aren't functions. And as you can see here, this figure 8 is not a function. However, it's still a mathematical relationship. And so what we're charged with the task to do is that there are 2 points given that are on this curve, and they want us to find the slope of the tangent at those particular points. Well, truth be told, we just have to take the derivative by using implicit differentiation. And then we're able to plug in the x and y values for the points, and then from there we could go ahead and once we have the slope, then we go from there. So let me show you how you could graph it on your textbook now, or on your TI calculator. The textbook actually gave us the parametric equations. Now remember, Mr. Adams said that parametric equations are a little better suited for mathematical relationships that aren't necessarily functions. And so what we do is we go into our calculator and put it in parametric mode. And what that does is that makes the x and y value dependent upon a third variable t. And we covered this before. You could take any Cartesian equation and separate it into 2 parametric equations. And it's not very difficult to do. But the book, our textbook, already did that for us. So I'm plugging in the square root of t squared minus t to the fourth, and then y equals t. So that's the first part of the parametric equation. And then the next part would be the negative square root of t squared minus t to the fourth. And then again, y would equal t. So these are 2 functions, and basically because we have a y squared term in our original Cartesian equation, that's how we would graph it. Now the only other thing that we need to do is set our parameters. Remember, both the x and y value are dependent upon t, and so I'm going to plug in like 0 to 20 for t min, t max. And I noticed that when I graphed it on my website, that the x and y value went from negative 0.5 to 0.5. However, I think I entered, oh yeah, I forgot the negative sign. So just so we could kind of make it fit, oops, hit the wrong button. I need to plug in for my x min like -1 and +1, and then for my y min I went from 1.5 to -1.5. And so if I let the calculator do its work, I see that I can only get the top half, so I'm going to change t to -10, and that seems to do okay. And there it is, the same figure 8. So that's what it looked like on my website. That's what it looks like on your calculator. But that's not what they ask us to do. But I always like to look at the graph, and they give us 2 points that we're supposed to plug in. And let me write these down real quick, and then I'll move the lights out of the way so you can see them. It's kind of hard to see with the graphing calculator in the way. And so we're going to have to figure out the slope of the tangent at root 3 over 4 comma root 3 over 2, and then at another point root 3 over 4 comma 1/2. And so this is based on these parametric equations that I entered into your calculator, and that's how you would graph it. So if you're taking the ACT or any standardized math test, remember that sometimes these mathematical relationships that aren't functions can be broken up into 2 parametric equations. And by the way, we could differentiate this too by differentiating the parametric equations. But the original equation is it's pretty easy to find the derivative of. We're just going to take the derivative of y to the fourth, which is 4y cubed. Remember, whenever we take the derivative of y, when we do implicit differentiation, we tack on the dy dx, and that's equal to 2y dy dx minus 2x. And so now what I'm going to do is I'm basically going to take every term that is going to have a dy dx in it and put it on one side of the equal sign and factor out the dy dx, and then divide both sides by 4y cubed minus 2y. And so then I get the derivative, is going to be, and I'll write this down on a new thing here, dy dx is equal to, if I factor out the 2, -2 over -2 times the quantity, -2y cubed plus y. And so we're going kind of fast, but you can look at the solutions in the Google Drive. But anyways, by canceling out the two negative 2's, I've got a simpler dy dx, x over y minus 2y cubed. And so to find the slope, I'm just going to plug in my x and y values that they gave us. And so what we're trying to do here is there's a point, there's one point here and one point here. I think the first one we'll do is the one up here, and that's √3 over 4, comma √3 over 2. So I've just got to plug those x and y values into my dy dx. Now, because of the square roots, we're going to have to kind of be careful, but basically I'm going to cube first. Please excuse my dear Aunt Sally. We'll do the exponents on the bottom. So √3 cubed is √3 times √3 times √3 over 2 times 2 times 2, which is going to be 8, right? So let's write that out. √3, √3, √3 over 2 cubed. And so 1 √3 times another √3 is √3 squared, which just gives you the base, which is 3. So then let's clean this up a little bit. I have √3 over 4 over √3 over 2 minus 2 times the quantity √3, 3 times √3 over 8. So by doing some cross canceling, I end up with √3 over 4 over √3 over 2, and then minus √3 √3 over 4, find the common denominator of 4. And then 2 minus 3 gives me a negative √3 over 4 on the bottom. So I have √3 over 4 over negative √3 over 4. And I'll slide this up in just a second. Let me write all this stuff down. And so if I slide this up here, you see that the slope was -1. So what I'm saying is that at the point √3 over 4, comma, √3 over 2, the tangent line to the curve will have a slope of -1. So we weren't asked in the textbook to write the tangent line, but I'm going to write it out. So the tangent line is going to have a slope of -1, and then when we plug it in the point slope form, we end up with -x plus 3 √3 over 4. So I'm going to take this and I'm going to plug it into my website here, and it should have a tangent line that touches at the point 0.433, I think is √3 over 4. So let me plug this in. Just take a second. It's a lot of work. I got to pull up the my square root symbol thingy. And there it is. When I graph it, there's the line. And guess where it zooms in at? Let me try and turn this point off. Click on it. The point of intersection is 0.433, comma 0.866. And just to kind of verify, because it's a decimal, I'm going to plug in my calculator. √3 over 4 divided by 4 is 0.433. That was the x term. And then if I multiply that by 2, I get 0.866, which is √3 over 2. And so that's correct. That's the tangent line, which means that's the correct slope. Now we just need to find the slope evaluated at the second point on the curve. And so we're going to use the same dy dx, and it's a little bit off the screen, you can't see it. But that was x over, well, here I'll write it out again. X over y minus 2y squared. So when I plug in the √3 over 4 and then 1/2 for y, I get √3 over 4. 1/2 cubed is 1/8. That 1/8 times 2 reduces down to 1/4. And then if I combine all of that, I get root 3 over 4. Have like terms. When you divide by a fraction, you multiply by the reciprocal, the 4's cancel, and I get the derivative is root 3. And that's pretty much it.